This is the first video in Topic 8 of IB Physics. Topic 8 is both HL and SL material. Take a moment and read the success criteria that we will cover in this video. So, a fuel releases energy, typically by a chemical reaction or it could be a nuclear reaction. One thing to really pay attention to is how the question is worded. Let's take coal as an example. If I'm using coal just to heat up my house, then it's a primary source because I'm using heat from the coal. But if I'm using coal in a power plant, where the goal is to produce energy for the consumer to use, we now have a secondary source. There have been quite a few questions lately, especially in the multiple choice, where it is very important to not think of other questions you've seen, but carefully analyze the question in front of you and answer that. So let's move on to specific energy and energy density. First of all, look very carefully at the units. In the past, these definitions might not have been as clearly defined. So especially if you're looking at past papers or different textbooks, these are what the IB are specifically going to use. Specific energy is the amount of energy per mass, whereas energy density will be the amount of energy per volume. Notice it's still about energy, and if we use our equation of density equals mass over volume, there is a relationship between these two. So here's a chart comparing specific energy and energy density of many different fuels. A couple things to think about. If a fuel has a very high energy density, it may be easier to transport because it'll take up less space. There's other things to consider: availability, the ease at which to ship it, and also how it's going to be used. Okay, so let's tackle a problem. I have a 250 megawatt coal-fired power plant, and it burns coal with a specific energy of 35 megajoules per kilogram. Water enters the cooling tower at a temperature of 350 Kelvin and leaves at a temperature of 293 Kelvin, and the water flows through the cooling tower at a rate of 4,200 kilograms per second. Now there are a couple of things I want you to keep in mind. First of all, Topic 8 is all about pulling the different subjects we've done throughout the course and putting them together in a... You don't really see a lot of new equations in Topic 8 because we're asking you to use them in new and different ways. So when you see a question and you think, oh my, I want you to stop and say, that's interesting. I haven't thought of that before. And then your second thought needs to be, Mrs. Henderson isn't crazy. What have I learned so far that allows me to tackle this question? Okay, so let's start with part A. Calculate the thermal energy removed from the water in the cooling tower each second. Notice the units. Okay, so we're heating up water, so let's use the information back from topic 3. Q equals mc delta T for heating up water. Now if I divide both sides by T, I'm going to get the heat per time, but that's okay because I'm also being given mass per time of the water going through our cooling tower. So if I put all these data in, I'll get 1,005 megajoules per second. Now notice I do have some extra sig figs here, and I'm doing that on purpose so I can carry it through later on. This is approximately 1,000 megajoules per second. But really, what is a megajoule per second? It's 1,000 megawatts, right? With a watt being joule per second. Okay, let's start part B. Assuming the only significant loss of energy is the thermal energy of the water, calculate the energy produced by the combustion of coal each second. Well, we've just calculated that we've got 1,000 megawatts being carried away from the water. But we also know that there's 250 megawatts being produced by this coal-burning power plant, given already in the question. So what does that mean for the total amount of energy per second? Must be 1,250 megawatts. Yep, sometimes it is just that easy. And finally, part C. Calculate the mass of coal burned each second. Okay, so if we take the total amount of energy that's being created, and I divide that by the specific energy, I'm going to get 35.7, but let's look at these units. Megajoules per second divided by megajoules per kilogram. Invert and multiply. And yes, that gives me the mass per second. Renewable versus non-renewable. I'm hoping this isn't new to you. It's really important you do have a few examples and you'll be able to apply your definition. So as I said earlier, one of the key things about topic 8 is all about energy transformations and applying a lot of the work you've done in previous topics. A few things to think about. What kind of transformations of energy have I used in this question? That will lead us on to efficiency and also the idea that nothing can be 100% efficient. Make sure you read questions carefully because sometimes they'll say, what additional places could energy have been degraded or released into the environment? Also, each type of power source or energy creation will have advantages and disadvantages. It's important that you go through each one and have a couple of really good examples to use for each case. And finally, we have these things called Sankey diagrams. They're a great way for us to visually look at how much energy has been added into our system and where it actually has gone. Not only that, the size of the arrows are proportional, which means they're done to scale. So in this particular case, you can see that the majority of the energy has actually gone to the cooling tower, and only a very small amount went into creating electrical output. The question we did earlier had only about 20% efficiency of that coal-burning power plant. In fact, I think most of them would be up to at most 40%. So let's think about how we can create our own Sankey diagram. Notice that this particular Sankey diagram has a grid behind it, which means it allows us to make scaled calculations. I don't know how much each box is worth right now, but if you look at the units being in megajoules, let's assume that one small box is 1 megajoules. In these questions, it's always important to write down the scale. Using the scale, I wrote down for each arrow how much energy must be used for each part. Notice 20 megajoules of energy was added in, 3 went to wasted energy, 1 electrical equipment, for example maybe the lights, and 16 megajoules were used to move the car. So if we go on to calculate the efficiency, useful output divided by total energy in, and if I want to do this in percentages, I'll multiply by 100%. In this case then I should get 16 over 20, which give me 80%. By the way, not very likely. Most cars would be more like around 20% efficient. So now's a good time for us to go back to that success criteria. Hopefully, now that you've seen this video, you can do all of these things.